So last class period, we started with the conic section stuff. And we looked at a few things. First off, we looked at a circle. And secondly, we looked at a parabola. And at the end, we were looking at ellipses. All right. And we saw some of the features of ellipses at the end of the last class. Specifically, we have a center at HK. Remember, we have 4 vertices at the end of our major and minor axes. Those are units away from the center in the case of the major axis, and B units away from the center in the case of the minor axis. We have 2 foci, which are C units from the center. C is found by the following equation in an ellipse. C squared equals A squared minus B squared. And there's this thing called eccentricity, which essentially is talking about how how stretched out the ellipse is. And that is determined by C over A. Okay. And in the last class, we did this one. We looked at example 7 and we found all of those components. So now we're going to look at the other. So remember, there's 2 types of questions with most of these conic sections. One is if I look at an equation, can I find the major components? And the second type of question is this one. If we're given some of the key features, can we find the equation? So this one says we have an ellipse whose vertices are 3, 1 and 3, 9. And it says minor axis is length 6. Now, these are the vertices, 3, 1 and 3, 9. As you can see, the distance between these 2 vertices is 8. So that's got to be the major axis. Between 1 and 9 is a distance of 8. So the major axis is going to be stretched out vertically, and the minor axis is going to be length 6. Now, be careful about this. If it's length 6, that means the total length of the minor axis is 6. So there's 3 on each side of the center. Just like because the total length of the major axis is 8, we know we're going to have 4 and 4 there. So because it's stretched vertically, more than it is horizontally, I know that my equation is going to look like x minus h squared over b squared plus y minus k squared over a squared set equal to 1. Again, because it's stretched vertically, I know that the larger number is going to be underneath the y part. Now, we can see where the center of this thing is based on having two vertices. I know vertex 3, 1 and vertex 3, 9. So halfway in between is the center. And you can go halfway in between 1 and 9, that's 5. Hopefully that's not too crazy. Also, because the length of the minor axis is 6, that means the B has to be 3. Because the length of the major axis is 8, that means the A has to be 4. Knowing this information allows me to complete the equation I'll take x minus 3 squared over 9 plus y minus 5 squared over 16 is equal to 1. I'm just plugging in my HK for my center, and then I'm plugging in the A and the B to get those denominators. So that's the equation I'm looking for based on the features that I was given. I was given two vertices and the length of the minor axis in that case. Let's try another one. This one says the center is at 0, 0. The focus is at 5, 0. And a vertex is at 6, 0. So we have the center, the focus, or a focus, I should say, and a vertex. So we have a center, a focus, and a vertex. Now, I like to again sketch what I'm doing here. If we're at the center of 0, 0, and my focus is 5, 0, and my vertex is 6, 0, well, that means the major axis is going to lie horizontally. So it's going to lie along the x-axis in this case. So the major axis is going to do that. And the ellipse is going to do something like that. Now, it's going to be symmetric. So if you wanted to find the vertex and the focus on this other side, you can choose, you can see that you move 5 units to the left, you'll get your other focus. You move 6 units to the left from the center, and you get your other vertex. But the key thing there is that because we're laid out or we're stretched out horizontally more than vertically, I'm going to use the equation x squared, or excuse me, x minus h squared over a squared plus y minus k squared over b squared is equal to 1. Now we need to find the HK. That's pretty straightforward because the center is 0, 0. So HK is the center, and that's going to be 0, 0. The A is the distance along the major axis from the center to the vertex along the major axis. So A is length from center to vertex on major axis. So in this case, that's pretty obvious. A has to be 6. Now I don't have B yet. So I need to figure out how to find B. And the way we find B is that the focus is at 5, 0. And we know that the focus is c units away from the center, where c squared equals a squared minus b squared. Again, for an ellipse, c squared is equal to a squared minus b squared. So I know well, first off, I know C is 5, right? We're 5 units away from the center. So we got 25 is equal to, A was 6, so that's going to be 36 minus B squared. If I take 36 minus 25, I get 11. And then if I add B squared to both sides, you get B squared is equal to 11. So if you wanted to, you could say B is the square root of 11. However, notice in my equation, the denominator is actually B squared. So if you didn't want to figure out that B was the square root of 11, that's all right. You can just plug in 11 for the B squared. All right, so that means that my equation is going to look like this. X minus 0 squared. I can just take x minus 0 squared, call that x squared. Divided by a squared. A squared is 36. Plus y minus 0 squared. Over b squared, which is 11, is equal to 1. And that's the final version of the equation for this ellipse. There's a lot of different ways to solve and find these features of your ellipse, or these features of the equation. All right, to find the A, the B, the H, and the K. Oftentimes, you can figure out a center by knowing halfway between two vertices. Sometimes the center will be given. If you have the two foci, you can go halfway between the foci as well. Is your center. So that'll give you HK. Your A and your B, those are coming from lengths of your major axis and your minor axis. The length of the major axis is 2A. That means that the distance from your center to your vertex is A. Or if you're talking about the minor axis, the length from your center to your vertex is B, and the length of your minor axis is 2B. Now, let's do another type of conic section. This will be the last non-trivial conic section that we look at. And this is the conic section of the hyperbola. Now, once again, we're going to have two different types of equations. And maybe at first pass, this looks like an ellipse. But the big difference between a hyperbola and an ellipse is that we care about this sign. This sign is a subtraction. So we're taking the same ellipse components. If we would have added here, we would have had an ellipse. But now we're subtracting and getting a hyperbola. Now, the key thing is, which one am I leaving with a positive coefficient and which one am I subtracting? I'll call, in this equation, I say the x minus h squared over a squared is the positive part, because when you square things, you're going to get positive numbers. And this y part is going to be called the negative part, because when you square things, you get a positive, and then you put a minus sign out front. So we're going to have a positive part and a negative part. In this first equation, the x is in the positive part and the y is in the negative part. In the other equation, it's the opposite. The y is in the positive part and the x is in the negative part. All right. So these are the two equations of hyperbolas. Now, I'll draw hyperbolas in just a moment to show you kind of what they look like, or I'll at least look at some things. Actually, let me just draw a sketch on the board. And then we'll talk through some of the information that we'll want to know. So we'll talk about a center, vertices, foci, and then we'll talk about asymptotes. So hyperbolas are going to look like this. This is like one hyperbola. Or like this. Now, the way I'm drawing these is I have not done a good job at drawing these. But the hyperbolas are going to point up and down, or they're going to point left and right. And it depends on which part is the positive and which part is the negative part, depending on which one is left and right and which one is up and down. So remember, we had two equations. One was x minus h squared over a squared minus y minus k squared over b squared equaling 1. So the negative part is the y component. That is this picture. Okay, you might ask, well, how can you tell that? Well, what if, let's just pretend our center is the origin right now. If our center was the origin, ignore the HK, the only way we could get something equal to 1, well, let me rephrase that. I could get this value to be 1. I could get the x component to be 1. So moving x over will allow me to hit, moving in the x direction, I can hit my hyperbola. Over here, moving up and down, I can hit my hyperbola. So that means the y part was the positive part. And I always forget on hyperbolas, it doesn't matter, but yeah, they use the a as always being the positive part, right? The denominator under the positive component. So there we go. Now, these 2 points here, those are the vertices. The center of the hyperbola, just like the center of an ellipse or the center of a circle, is not actually a point on the hyperbola. Just like the center of a circle is not on the circle. Just like the center of an ellipse is not on the ellipse. The center is that point in between. And for hyperbolas, we actually have 2 foci. We have one focus up there and one focus down here. Obviously, if you rotate this picture 90 degrees, you get this one. Now, I'm going to look at this via Desmos as well in just a moment. But I want to point out that these might look like 2 parabolas right now, but they're not exactly that. They look like parabolas close to the vertex. But as we get further and further away, they're gonna actually look like lines. And what you'll be able to do is you'll be able to draw a line through the center that's going to be an asymptote for the hyperbola. So that's what we're talking about when we're referencing asymptotes there. Okay. So that gives you kind of a good picture of what's going on. Center is at HK. Vertices are A units from the center. Notice that A was always underneath the positive parts, right? And if the A is underneath, or excuse me, the positive part is the Y, then we move up and down till you hit the vertices. If the positive part includes the X, then we move left and right to hit the vertices. And the same thing with the foci. Whichever direction you move to hit the vertices, you also move to hit the two foci. Now, here's the thing that you should highlight or asterisk or whatever. In terms of hyperbolas, the C that you're using for your foci now is a different formula. In this case, for hyperbolas, C squared is equal to A squared plus B squared. Remember, ellipses were A squared minus B squared. So now we once again change the sign and we have A squared plus B squared for hyperbolas. That gives me my C squared. Those asymptotes I was talking about are going to have slopes positive, negative B over A or positive, negative A over B, depending on which type of equation. If we had to move A units up and down, then A is going to be in our numerator. If I had to move A units left and right for the vertices, then A is going to be in my denominator. And then once again, the eccentricity is simply going to be C over A. So in the ellipse, the eccentricity meant how spread out or how stretched out the ellipse was. In a hyperbola, the eccentricity means something similar. It's going to be how flat is the hyperbola. Now, before we do a problem, I want to take a look at a hyperbola. So here's a hyperbola. And we'll graph. The hyperbola is y squared over 25 minus x squared over 16 is equal to 1. And as you can see, since the positive component includes the y, and we have a 25 under that, we've moved 5 units up and 5 units down to hit the two vertices. If you calculate your C for your foci, it's going to be 25 plus 16 underneath the square root. So you get about 6.40. So there and there are going to be your two foci. Now, here's what happens. If you're looking at a point, on my graph, so I look at a point on this hyperbola. There's a random point. And I measure the distance between the point and one focus. And then I measure the distance from the point to my other focus. So I have two distances here. A distance from a point to a focus, and a distance from that same point to my other focus. Instead of adding them together, like we did with the ellipse, let's subtract these two distances. So it turns out the first distance, in my case, that's the smaller one, is about 2.007. The bigger distance is what I call D2. It's about 12.007. If you subtract those, you get -10. Now watch what happens if I move the point around. The two distances are changing. Now they change to 11.94 and 21.94. But when you subtract the two distances, you get 10 or -10, depending on how you subtract. And that happens for every single point on the hyperbola. That when you subtract the 2 points on the hyperbola, or subtract the two distances, while the distances are going to be different, the difference in their distance is always going to be 10 or -10, depending on which way you subtract. So that's one of the key features of the hyperbola. Now, I want you to notice that as we zoomed in, it kind of looked like parabola shape here at the corners where they turn. But if you start zooming out, all of a sudden you'll see that these lines actually become pretty straight looking. And if you created a line, now because A is 5 and B is 4 and A is underneath the Y value, if you created the line Y equals 5/4 X, you'll see that that line is an asymptote to the hyperbola. And the other asymptote to this hyperbola will be -5/4, Y equals -5/4 X. Change that setting to red. Okay. So while they kind of look like parabolas at the corners where they turn, if you zoom out, they start looking close to intersecting lines. And they get straighter and straighter and straighter looking as we move away. So that's how parabolas work, and that's geometrically the key feature. Geometrically, the key feature is if you look at the distance between, or excuse me, the difference in distances from point to focus 1 compared to point to focus 2, it's going to be a constant. All right, it won't always be 10. In this case, it was 10 because my A was 5. But in general, that difference is always going to be 2A. All right. So now that we've seen some hyperbolas, let's do what we always do, which is look at an equation of a hyperbola and pick off some of the key features. We want to find the center, the vertices, the foci, and the eccentricity. If you also wanted to find the asymptotes, you could do that too. We don't need to in this class. Here our hyperbola is y plus 3 squared over 225 minus x minus 5 squared over 64 equaling 1. Now again, the positive part involves the y component. The negative part involves the x. So that means this hyperbola is going to point up and down. Right? It has to do that since the positive is with the y, or since the y since the y is in the positive part. Okay. Now, I just want to point out that here, A squared is going to be 225, which means that A has to be 15. B squared, since that is 64, that means B has to be 8. Again, A and B are always going to be positive, so when you say A squared is 225, you can always just take the positive square root of both sides. All right, so let's start looking at these things. The center, well, this is x minus 5. So the x value is going to be 5 for the center. The y value is going to be -3. Again, be careful with that. It's always y minus k. And also be careful that you don't flip the x and the y. The 5 is with the x. The -3 is with the y. The vertices. On a hyperbola, there are 2. And because the positive part's here, I move up and down . from the center A units. Everybody understand we're moving up and down because our hyperbola looks like this, because the positive part has the y in it. So I'm going to take 5, -3, and I'm going to adjust the y value up and down by 15. So the upper vertex is going to be 512, and the lower vertex is going to be 5, -18. Now, to get the foci, they're going to be C units up and down from the center. And in a hyperbola, remember that C squared is equal to A squared plus B squared. So I have to figure out what C is before I get the foci. A is 15, so A squared is 225. B is 8, so B squared is 64. 225 plus 64 is 289. If I take a square root of 289, that actually does give me a whole number. By the way, you won't always get a whole number. So if you get a rounded number, or so if you get a ugly decimal, just round it to a couple of decimal places. In this case, I got a whole number, which was 17. So if I'm getting my foci, I'm going to take my center, which is 5, -3. And to get the upper focus, I add 17. To get my lower focus, I subtract 17 from the y component. And then the last thing this asks me for is the eccentricity. Oops. Which again is C over A. I just found the C to be 17. And we knew the A was 15. By the way, 17 over 15, you'll notice, is a little bit above 1. Remember that when we found the eccentricity for ellipses, they were always between 0 and 1. And that was how stretched out they were. Well, for hyperbolas, eccentricities are always going to be above 1. And we'll talk about eccentricities in general in just a moment, but hyperbolas, we're gonna get eccentricities that are above 1. So that's how we use the equation to find those key components. Now, we're gonna do the reverse. We're gonna be given a couple of key features and use those key features to find the equation. This says find the equation of a hyperbola whose vertices are 2, 3, and 2, -3. And we know that a point on the graph, another point on the graph other than the vertices, is the point 0, 5. So we just know the 2 vertices and the point on the graph. Now, you might not think this is a lot of information, but from this information, we can get all the components for our equation. First off, if you draw the vertices 2, 3, and 2, -3, since they are up and down, since they're vertical change to get to each other, I know the hyperbola has to point up and down. Now, what else do we know just based on the vertices? Well, since vertices are equidistant from the center, we can find the center by going in between the vertices. So that means the center is the point 2, 0. Right? Hopefully everybody sees that. Has to have x value of 2. And then halfway between 3 and -3 is 0. That should be fairly obvious. What else do we know? We also know A is the distance from the center to a vertex. So in this case, A has to be 3. From the center to a vertex is 3. So given those 2 vertices, that gives us a lot of information about the equation. We know now that since we're pointing up and down, the y is going to be in the positive part and the x is going to be in the negative part. A is always the one underneath the positive part. So we can figure out the HK. Y minus 0 squared over 3 squared minus x minus 2 squared over, I don't know b yet, so I'll just leave that as b squared. I'm going to clean this up a little bit. Y squared over 9 minus x minus 2 squared over b squared is equal to 1. So I know everything except for the b. I know everything except for the b. How do I find the b? Well, I know a point on the graph is 0, 5. And I'm just gonna pretend it's there. That means if you plug in 0, 5, you should get a true statement. So let's do that. 5 squared over 9 minus 0 minus 2 squared over b squared is equal to 1. And now I can use this equation to solve for b. (25 over 9 minus 4 over b squared is equal to 1. I would subtract 25 over 9 from both sides. That would give me, I'm going to write it this way, negative 4 over b squared is equal to, if you take 1 minus 25 over 9, and then convert that into a fraction, you get 16 over 9. So, or negative 16 over 9. So you get that. Since you have two fractions equal, you could cross multiply. Let's cross multiply. Negative 36 is equal to negative 16b squared. And then I divide both sides by a negative 16. The reduced form of that fraction is 9/4. So 9/4 is b squared, and then b would be 3 over 2 if I wanted to take the square root of both sides. Now I'm leaving this as a fraction. Obviously, if you wanted to write this as decimal, you could do that. 2.25 is the decimal. But all of that means, now that I know my b squared, now I know my equation. My equation is y squared over 9 minus x minus 2 squared divided by 9/4 is equal to 1. Again, there's other ways to write that equation, but that's about as good as it goes. So if you're ever given a point on the graph, what you can do with that point is always plug it in. And since if you only have one thing to find, you can plug it in and find that one thing. All right. I want you to try this one on your own. This one will be a little bit easier than the previous example. Less work. It gives you your focus, your vertex, and your center. I should say one vertex, one focus, and your center. All right, let me go through this one. All right. So we know the center is at the origin. And we know the vertex is at 0, 2. So that alone tells me that we're pointing up and down with our hyperbola. Which also tells me that the y is going to be in the positive part and the x is going to be in the negative part. Now, the other thing we have is that the focus is at 0, 4. Now, with all of those things, Excuse me. You can do this in a lot of different ways. Okay, you can start, stop, and pick up. I'm just gonna say, we know that we point up and down. We know that our hyperbola points up and down. So it's going to look like, the equation is going to look like this. All right. Since the center is at 0, 0, we know the h and the k are both going to be 0. So center is always hk. So we know that. The vertex is 0, 2. And the vertex is a units from the center. So that means a is 2. Now, a focus is c units from the center. Since our focus is at 0, 4, that means our c here has to be 4. Now, the c is not what goes into my equation. The b is what goes into my equation. And I can find that, remember, with a hyperbola, c squared is a squared plus b squared. Again, you always have to be very careful when dealing with ellipses. This is a squared minus b squared. When dealing with hyperbolas, this is a squared plus b squared. So c being 4 gives me a 16 there. A being 2 gives me a 4 there. That means b squared has to be 12. And b would be the square root of 12. So now I can write the equation. K is 0. So I'm getting y minus 0 squared divided by a squared. A is 2, so a squared is 4. H is 0, so x minus 0 squared is going to be just x squared. B squared, now we know is 12. B is the square root of 12. And that's equal to 1. So that's the standard form for the hyperbola with those features, with the center, vertex, focus that was given. Now, the last thing we're going to do is this. So I've been giving you equations of conic sections and stating, well, what are the key features of this hyperbola? What are the key features of this ellipse? What are the key features of this circle? What are the key features of this parabola? And most of the equations that I've been giving you have been in standard form. Like this was the standard form for an ellipse. This was the standard form of a hyperbola. With the parabola, we didn't start out with standard form, but we got standard form by completing the square. In example 1 with the circle, we had standard form of a circle. But remember, all conic sections algebraically can be written this way. That's not standard form for most of them, except in very, very rare cases. So if we're given a conic section, how can I tell what the conic section actually is? How can I tell whether it's a circle or a parabola or an ellipse or a hyperbola? And the key thing to do is to look at the squared terms. So if you look at a circle and you were to square this thing and square this thing, well, you would end up with an x squared plus a y squared on the left. So you'd end up with an x squared plus some other terms, and you'd end up with a y squared plus some other terms, equaling a number. Now, we know that anytime you want to deal with equation equivalencies, you could multiply both of those sides, both sides, by a number. But whatever you multiply by, the number in front of the x squared and the number in front of the y squared are going to match up. So with a circle, if x squared and y squared are on the same side with the same coefficients, so if I can write my x squared term and my y squared term on the same side with the exact same coefficients, I know it's going to be a circle. Now, what about a parabola? Well, in one type of equation on the parabola, if I multiply this out, I'd get an x squared term, but there would be no y squared term. On this other equation, I'd get a y squared term, but no x squared term. So the conic section is going to be a parabola if I have one of the x squared or y squared terms and don't have the other. So you have an x squared but no y squared, or you have a y squared but no x squared term. What about an ellipse? Well, an ellipse we get something like that. obviously we could do this minus h minus k and then square it out and all that stuff. But with the ellipse, the a and the b are different. However, notice that they're both going to be positive, whereas in a hyperbola, one's going to be positive, one's going to be negative. Now, here's the tricky part. You can actually multiply by a number, right? That number could be positive or it could be negative. If you multiply by a negative on the left and right up here, then both of these terms have a negative coefficient. So we get an ellipse if x squared and y squared are written on the same side. Coefficients are either both positive but different, or both negative. So if the x squared and y squared terms are on the same side, and the coefficients are both positive, it's an ellipse. If the x squared and y squared terms are on the same side, and the coefficients are both negative, then it's an ellipse. And lastly, we get a hyperbola if x squared and y squared written on the same side with coefficients such that one is positive and one is negative. So if we have any other forms other than our standard forms, then we're able to figure out which one of these four conic sections we have. Now, by the way, I think I mentioned this last time, but I'm going to mention this again. These are the four conic sections which are non-trivial. And by non-trivial, I mean they have squared terms. If you don't have a squared term, then you just have a line. So we don't deal with that too much. What I mean by that is if A, B, and C are all 0, then we just get dx plus ey equals plus f equals 0, which is a line. So I mentioned that earlier last time. So these four conic sections are what we often call the non-trivial ones. All right, the ones that are most interesting. So that's how we identify conics. We pay attention to the squared terms. A circle, if I can write x and y on the same side and they have the same exact coefficients. A parabola, if one of these x squared or the y squared is missing. I have one but not the other. I have an ellipse if the x squared and y squared term can be written on the same side and both of the coefficients are positive or both of the coefficients are negative. And then I have a hyperbola if we write x squared and y squared terms on the same side. And one is a positive and one is a negative. So let's take a look at these. And I think what I'm going to do, rather than write them on the board, is I'm simply going to copy and paste these into a Word document. And I will write what each one of these is. I'm getting all my measures and stuff. There we go. Weird. There. All right, that's better. So look at this first one. With this first one, the x squared term and y squared term are written on the same side. They both exist. The coefficient of x squared is the number 1. The coefficient of y squared is the number 4. So since they're not the same, it's not a circle. Since I have both of them, it's not a hyperbola. Since they are both written on the same side, and we have different coefficients, but they're both positive, that's an ellipse. For the second one, fairly obvious. We have x squared and y squared written on the same side. One coefficient is positive, one coefficient is negative. That's a hyperbola. For this third one, we have y squared, but no x squared in sight. So that has to be a parabola. There's no x squared. This one, this fourth one, we have 25x squared, but no y squared. So that's a parabola. This one, x squared and y squared are on the same side, and they have the exact same coefficient. In this case, that's 4. So that is a circle. Now, these last two are a little bit tricky because I have to think through what's going to happen when I square this. Well, I'm going to get a few terms, but one of them is going to be x squared. And what's the coefficient of that x squared going to be? Well, when I multiply through, it's going to be a 3. So I can really think of this as 3x squared. Over on the other side, this is 2y squared when I multiply things through. So, in other words, I'm going to get 3x squared plus some other stuff on the left is equal to 6 plus 2y squared plus some other stuff. That's what I'm trying to say. And then beyond that, you have to say, oh, these are not on the same side of the equation. They're on different sides of the equation. So if I were to put these on the same side of the equation, the 3x squared, I'll leave on the left. I'd have to subtract 2y squared from both sides. and then it's easy to see. Now, most of us will be able to do that in our heads. Just to say, oh yeah, the x squared's on the left, it's got a coefficient of 3. The y squared's on the right, coefficient of 2. So if I put them on the same side, I'm going to get 3x squared minus 2y squared. And now I can see, oh, x squared, y squared on the same side, coefficients. One is positive, one is negative. That's a hyperbola. So in our original equation, that had to be a hyperbola. By the way, these other stuff, I'm writing it so that other stuff is not going to contain any squares in them. So some people like to just put ... There's all kinds of different ways you can do that. But that's a hyperbola. For the exact same reason, when you multiply things out on this last problem, you're going to end up with 9x squared plus 4y squared if I put things on the same side. I have a 9x on the left, a negative 4y squared on the right. Nine x squared, 4y squared on the same side means that that's going to be an ellipse. So if we're focused on the x squared and y squared terms, then we can quickly identify which scenario we are in. And if I know which scenario I'm in, if I know I'm dealing with an ellipse here, then I know what type of form that I'm trying to transform it into and what it's going to look like at the end. So with the ellipse, I know what type of standard form of the ellipse looks like. With the hyperbola, I know what the standard form of the hyperbola looks like, and so on and so forth. So identifying conic sections, or being able to do that quickly, is a nice thing to know in general. Now, the last part of conic sections that we're going to deal with is the eccentricity. The eccentricity in both the ellipse and the hyperbola, we calculated as C over A. And in the ellipse that we did, we saw the eccentricity was somewhere between 0 and 1. And in fact, because of the way C is computed, it's always going to be like that. We also saw in the hyperbola that the eccentricity we got was above 1. And it turns out the eccentricity of a hyperbola is always going to be above 1. Let me talk about that and some of the reasons why. So what we said as far as eccentricities go, for the ellipse, the eccentricity is always going to be between 0 and 1. That's because the eccentricity is C over A. And when we calculated the C, we did A squared minus B squared to give me the C squared. That always means A is going to be bigger than C. So if the denominator is always smaller, if the denominator is always bigger than the numerator, we get this fraction, which is less than 1, but they're both positive, so they're going to be greater than 0. With the hyperbola, the eccentricity is always going to be above 1. And that's because the eccentricity was C over A there, but the C came from this other equation, A squared plus B squared equals C squared. So in this case, the A is always smaller than the C. A plus something is equal to C, so C has to be bigger. Right? C has to be the bigger of those two numbers. So for the ellipse and the hyperbola, the eccentricity is always between 0 and 1 for the ellipse. The eccentricity is always above 1 for the hyperbola. Now, I want you to think about the standard equation for a circle. You don't have to write this down right now. If I were to divide both sides by r squared, I would get essentially the equation for an ellipse, but with the A and B both being 1. Or both being the same, sorry. A and B both being the same, excuse me. Doesn't have to be 1. I'm thinking of the ratio, but the A and B are the same there. What would happen with the eccentricity if A and B were the same numbers with this ellipse? If A and B were the same numbers, and this does look like an ellipse where A and B are the same, then that C would be 0. So some people will say, well, a circle is a special type of an ellipse where A and B are the same. What we did is we defined the circle to be where A and B were the same, or the R, but the ellipse is when A and B are different. But in other scenarios, people will define a circle is a special case of an ellipse where A and B are the same. And therefore, if we apply our understanding of the eccentricity of an ellipse, if A and B are the same, then the C squared becomes 0, and the eccentricity would be just 0 over whatever the A is. So the circle actually has eccentricity of 0. That's all I was trying to get at. And it turns out the parabola has an eccentricity of 1. So going from the ellipse to the hyperbola, in between eccentricities, when eccentricity is 1, we get a parabola. So that's the algebraics behind the eccentricity. I want you to understand a little bit more about where this concept comes from. And we're going to go all the way back to the very first thing we wrote on the board. Let's pretend I'm talking about conic sections being cut from a cone. If I take a plain piece of paper and I cut the cone like this, hopefully that you can see that. If I cut the cone flat, that's going to give on my piece of paper a perfect circle. All right. Notice that the way I cut this, my plane, or the way I drew my line, it's a line with slope 0. Now let's start adjusting how I draw that cut. Again, we're going to think about cutting with a piece of paper straight. And now we're going to say, what if I adjust this a little bit? What if I'm a little bit skewed? So if I'm a little bit skewed, but we're still going through both sides, through the same side of the infinite cone, what that's going to do is that's going to give me an elongation of a circle, which is an ellipse. Notice that that's going to happen anytime I'm cutting through this, just this side of the cone. And that's going to happen when the slope of this cut line is between 0 and, well, even with this parallel with this line. And generally, we make that line have slope 1. What if my cut line is exactly parallel to this side of the cone, or to any side of the cone? Well, if my cut line is parallel to the side of the cone, you can guess what we're going to get. We're going to get a picture that is a parabola. And what if my cut line goes through the cone at such an angle that it's actually steeper than this? So in other words, if it does something like this, and then cuts so steep, it's gonna cut through the other side. Again, we're just talking about a paper shooting straight out at us. Well, that's where we get our hyperbola. So some people think of eccentricity not so much in the algebraic sense, but in the cutting of the cone. What's the angle of the plane where I cut my cone? If the angle of the plane is 0, then I got a circle. If it's between 0 and 1, then I have an ellipse. If it's parallel to the line, I have a parabola. And if it's like this, steeper than the side of the cone, I get a hyperbola. Now, all of the ones that I did were cutting through the cone at a place that was not this middle. If you cut through the cone at the middle, that's where you get the trivial conic sections. Because if I cut through the cone in the this point, I end up with just getting a point. If I cut through at the point, but parallel to this line, I just get a line. And there is a weird scenario where I cut through exactly here. And I end up just getting 2 intersecting lines. So the trivial conic sections, which are lines, intersecting lines, points, and a single line, those happen when you cut through this point on the cone. Non-trivial conic sections happen when you cut anywhere else. All right. So you should know what eccentricity is and then where it comes from. And again, I like both the algebraic sense. You can determine whether the eccentricity is 0, between 0 and 1, above 1 or 1, using some algebra and what we know about C, what we know about relations between the circle and the ellipse. Okay. You can also do some hyperbola stuff and parabola and figure out that it's 1. Basically, you just let your B be 1, or your B be 0 on one of those, because you don't have a square term. But it's a little bit weirder, So, so you can think about eccentricity that way, or you can think about it as how a plane intersects this cone. If it's slope 0, we get a circle. Anything between 0 and 1, we get an ellipse. Once we're parallel to this line, our slope is 1, and so we have a parabola. Once our slope is greater than 1, we cut through both sides of the cone, and we get a hyperbola. And I like seeing both of those methods, both the algebraic and just looking at the cone. Now, I spent a lot of time talking about conic sections, both today and last class period. In the next few things we're going to do moving forward, it'll probably be a little bit quicker. We're going to go a little bit quicker, but there's a lot of information in that conic section part. So that homework is due Friday at 5. Make sure you get that done. and then we'll start on the next section, on the next material, next class period. All right, see you then.